My name is Professor Stephanie Colby, and we're starting off with Chapter 1 in your textbook. So, when you think about astronomy, what do you think of? What comes to mind? Why did you actually take this course besides you needed it for credit? What are the things you think of? Do you think of stars, dark skies, a childhood memory? I want you to think about what does it mean to you as we start learning about what you're going to learn in this class. Okay, so just an overview of what we're going to learn overall in this class, okay? We're going to dive into the depths of our solar system. So we're going to learn not only a little bit more about our planet Earth, we're going to learn a lot about our sun, and then all other planets in our solar system. Can you name all the planets in this image? So let's see. Our sun, Mercury, Venus, there's us, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then technically here's Pluto, which isn't really a planet anymore, and we'll discuss that in this class. We're going to learn about not only our sun, but other suns out there. Our sun is just a star. It's a main sequence star, fairly typical in mass and size. But we'll talk about how stars are born, how other solar systems we believe have come to be, and we'll talk about different properties of stars. When it comes to stars, learning about their life and evolution is really interesting, but a lot of people get more fascinated with stellar death. So these are 3 different images of different ways that a star might die. A star might die as a planetary nebula. Our sun will probably die as a planetary nebula. A supernova explosion, or they might end up as things as neutron stars or pulsars, or even black holes. We're going to dive into cosmology and galaxies. We'll learn about our own Milky Way galaxy. Here's an artist's rendition of the Milky Way galaxy, the kind of basic properties of our Milky Way galaxy. We'll talk about other galaxies close to us, like the Andromeda galaxy, and groups of galaxies. And then we'll talk a little bit about how we believe our universe formed, how we think it's expanding, and what we think the ultimate fate of our universe might be. Okay, so Chapter 1 in your textbook, a modern view of the universe, or like what I like to say is the science of astronomy. So throughout the lecture notes, you're going to see these concept questions. I want you to pause the video during these concept questions and take a moment to think about the answer for yourself, and then press play again to see the answer. So which of the following major branches of science does astronomy use? Physics, chemistry, earth science or geology, or all of the above? What do you think? So what's really cool about astronomy is astronomers use all the different branches of science. And when it comes to physics, astronomy is all about physics, okay? Astronomy, in terms of its fundamental basic properties, is intertwined with the fundamental laws of physics. So when we talk about the orbits of planets, the distribution of matter in the universe, we're talking about laws of physics. When it comes to chemistry, we want to know what a planet is made of, what the atmosphere is made of, how reactions are happening within the central regions of stars. We're talking about chemistry. When we start looking at planets in our own system, or even extrasolar planets, we rely on the geology of Earth as a comparison to know what we're looking at or what we might hope to see on other planets. There's also one I didn't put on here, which would be biology. Astrobiology is a huge field where we use the principles of biology for a potential understanding of what life, extraterrestrial life, might be like. So, to dive into any field, it's important to have a good understanding of scientific measurements. So let's start with this question. If I asked you, how tall are you? What measurement of unit comes to mind first? So just answer the question really quickly. How tall are you? Did you answer your question did you answer this question in terms of meters, centimeters? Hopefully not quarts, or feet. So I grew up in the United States, so when I think about how tall I am, I'm 5'6". That's 5 feet, 6 inches. You may, however, thought you were in so many centimeters or meters, okay? So in the United States, we use the old British system of units. That's feet, pounds, quarts, and seconds. Really, we're one of the few countries that still uses this system. Most countries, and including all scientists, use the International Systems of Units, or called SI units. And for everything we're going to talk about in this course, we're going to stick to SI units. So this will be meters, kilometers, centimeters, grams, kilograms, and seconds. What's really lovely about the SI units is that they are organized in such a way that the multiples or fractions of any unit can be easily expressed in terms of what we call powers of 10. This allows us to display really big numbers or really small numbers in a more comprehensible manner. So when we start talking about the scales of the universe, we're going to talk about small to big. Now, there's a scale of the universe video that's available to you on your module this week. And there's also a kind of scale simulation that I have available to you that you should check out in your module this week. We're going to talk about, on the smaller side, the scale of our own solar system, looking at the sizes of our planets, of our moons, and moving outwards. We're going to move to larger and larger distances, like out to the distances to the nearest stars, then out to the very reaches of our own galaxy, and then further out to the observable universe. So we start talking about really big numbers in this class. And one of the easiest ways for us to display such big numbers is through using powers of 10. So powers of 10, multiples of 10. So if we had 10 to the power of 0, that would just be 1. 10 to the first would be 10. 10 to the second, or 10 squared, is 100, and so on. Now, this also can go to the small measurements as well, which works really well for other sciences. 10 to the negative 1 is 0.1. 10 to the negative 2 is 0.01. We'll see these smaller numbers when we start talking about electromagnetic radiation, because we're going to talk about electromagnetic waves that are both really tiny and really large. So, powers of 10 notation, okay, allows the number of significant figures to be clearly expressed. In addition to compressing a really large number, instead of seeing all those zeros, we can represent it in terms of powers of 10. So for example, the distance to the Andromeda Galaxy is about 2.54 times 10 to the 6 light years. We'll talk about what a light year measurement is in a little bit. Now we could, on the other hand, represent this as 254,0,0,0 light years. Okay, this isn't even that far of a distance in this case, but you can see already that it's much more clear to represent in terms of powers of 10. So here's a good scale size for you. On the small size, like the fundamental properties that make up everything, our atoms and the protons within those atoms, you have 10 to the negative 15. All the way up to the size of the observable universe, 10 to the 25th power. You have the powers of 10 video available to you in your module this week, so please take a moment to watch that video. Okay, so here's a concept question to just get you on the right mind frame for these powers of 10 notation. So which is the correct representation of this scientific number? So here's written out in long form. How would you write this in scientific notation? Okay, so if you didn't get this correct, you might have needed to know one other key thing about scientific notation. You always want to represent the first number, the front number, between 1 and 9. So you would not write this as 567 because that's larger than the number 9. So you would need to represent this front number between the number 1 and 9. Okay, so let's give it another try. So which is the correct representation of this scientific number? Notice where the decimal place is. All right, hopefully you got this right. Easy way I like to do this is when you know the decimal place is, you count over to know your power of 10. So 1, 2, 3, 4, 5. If I went one more, that number would be less than 1, so I have to stop at 5. So 9.0 times 10 to the 5th. Okay, so in astronomy, we start talking about really far distances. So we've actually come up with a few new units to represent distances. One of these units is the astronomical unit, or the AU. It is the average distance from the Earth to the Sun. 1 AU is about 1.5 times 10 to the 8 kilometers, or 93 million miles. So astronomical units are really good for measuring distances within our own solar system, because what it is we're really saying it's just the distance from the Earth to the Sun. So therefore, that distance, we want to know the distance to Jupiter, we could represent that in terms of AU, or astronomical units. But to represent distances that are even further, okay, let's say to the nearest star, we would use the unit of a light year. A light year, represented as Ly, is the distance that light traveled in 1 year. Now it's important to know that the speed of light, or little lowercase c, is equal to 3 times 10 to the 5th kilometers per second. This tells us that 1 light year is 9.5 approximately times 10 to the 12 kilometers, or about 63,000 astronomical units. So a little side note about this, okay? The speed of light, okay, is the speed of a photon, how fast a photon is moving. So a light year is determined by how far, meaning in distance, a photon of light travels in a certain amount of time, in this case 1 year. So how far a photon travels within 1 year. And this is coming from just the basic understanding that speed, okay, is distance per time. How far you go over how much time is how quickly you're going. So a light year is the distance that a photon travels in 1 year, knowing that a photon travels at the speed of light of 3 times 10 to the 8 meters per second. Okay, so light years are really good for measuring like to the nearest star. But let's say you want to go to the nearest galaxy or beyond, we use the unit of a parsec. A parsec is the distance at which 1 astronomical unit spans out an angle of 1 arc second. So I'll tell you what arc seconds are in a minute, but just notice it's an angular measure. So notice in our image here, here's the sun and here's Earth's orbit. So Earth orbits around our sun in almost a circular path. So notice the distance from the Earth to the sun, right from the sun to the Earth's blue line here, that measures 1 astronomical unit. Now, if you are really far away, here you are as the observer, and you're looking at that distance, and you notice that it observes to you that that distance is only what we call 1 arc second, which is a fraction of a degree. It only takes up that much angular size. That's what we call a parsec. So a parsec means you have to be that distance away to see 1 astronomical unit spanning out only 1 arc second. So we can define a parsec as 3 times 10 to the 13 kilometers, or 3.26 light years. So parsecs are really good for our really far distances, like to other galaxies or further. So the farther away we look back in distance, the farther back we look in time. That's one of the really cool things about astronomy is you're almost like time travelers. Because light does take a certain amount of time to get to us, right? It only moves at a designated speed, the speed of light. So when we're looking at objects that are hundreds of light years away, it actually takes light a long time to get to us. It's not instantaneous. So that means that the light that we're receiving actually was emitted from that object many years ago. So in a sense, we're looking back in time when we look at objects in the night sky. So the scales of the universe, to kind of get your head around that again, these 2 videos, the Morgan Freeman version, okay, is a little bit more updated, and that's the one I've provided you on our module page on Canvas. You can also watch the 1970s version. It's kind of fun, got some fun music in there for you. But please at least watch the one available to you on your Canvas page. Okay, we're going to dive into Chapter 2 briefly, but know that we'll cover the rest of Chapter 2 next week in your module. So take a look at this image in the back here. This is actually Mauna Kea in Hawaii. But notice that the stars above Mauna Kea, they look like they're moving in a circle. So this is a time-lapse photo, meaning that we took an image and we left the shutter open for a long time. So the stars appear to move in what we call star trails. But the stars aren't moving. It's actually the Earth that is spinning. And in this case, we're pointed towards the North Star called Polaris. And so our Earth is rotating on an axis. And our axis points towards what we call the North Celestial Pole, or towards the North Star called Polaris. So when the Earth spins on its axis, it appears that all the stars orbit around us. And so if we leave our camera shutter open, it looks like the stars are moving in circles around above our sky. So when you look at the night sky, I'm sure you've heard of constellations. But what really is a constellation? So you look up and you see all those stars, and you know that somewhere someone has designated some pattern to those stars. And that's what we call these constellations. So if you look up at the night sky without any binoculars or telescope, just with your naked eye, you can see about 3,000 stars above your horizon. So the horizon is defined as the line right where your land meets your sky. So the easiest way you can think of a horizon is like on the ocean where the water meets the sky. That's your horizon, but it's really anywhere. Wherever the land meets the sky is your horizon. So when you look up, you can see about 3,000 stars. That means there's also 3,000 stars below you in the southern hemisphere. So if you could look over all the stars on Earth, you could see about 6,000 stars. And that's just limited by how powerful your eye is. So when we look at the stars, many different ancient civilizations saw different patterns in the sky, and we call these constellations. There's 88 constellations in the night sky, and that's because every inch of our sky is designated by a constellation. So notice that you see the constellation Orion here on the left. That's how you might see it in the night sky. But really the constellation is everything within this yellow boundary. Okay, so here's the blue outline. That's the constellation. It's supposed to look like this guy over here, right, with a big club. Okay, and he's got a belt and a sword. So you might be able to see that. Here maybe the head and the belt and the sword. But the blue lines are outlining the brightest, most prominent stars in the constellation. The blue line is what we call an asterism. But really, every star within this yellow line is technically within the constellation of Orion. So where the blue lines are outlining the major constellation that you've probably seen in other books, those are connecting the dots effectively through the brightest stars. All these other stars in here, within the yellow line, are contained within that constellation. And those yellow lines make up the entire night sky. So every star in the night sky is technically within a constellation. So you can think of these constellations like states of the United States. So imagine the United States is the entire night sky. So all the surface area of the United States is broken up into states, right? So the states are the constellations. The states are these yellow lines. Now we have our brightest cities, right? Okay, the biggest cities, the capital cities within the states, make up the primary stars of the constellation. But all the small cities within the state are also included in the state, just like all these small stars are included within the constellation in the bounds of this yellow line. So there's 88 constellations that make up the entire night sky, and every star is in a constellation. So here's what I was trying to represent. In this case, the red line is the states, okay? So notice that the constellations all butt up against each other, so that every portion of the night sky is covering with a constellation. So when we look up in the night sky, it appears to us that all these constellations sit flat relative to our position. And that's because they look like they're sitting on this sphere around us. And we call this sphere the celestial sphere. So the celestial sphere is just a projection of our circular Earth. And that's where the stars appear to sit. That's where the sun appears to sit and the moon appears to sit. But this sphere is fictitious. It doesn't really exist because the stars are several light years distance away from us, and the moon is closer to us than the sun, but they appear to be at the same distance from us in our sky because they appear to sit on this celestial sphere. So we've talked about the celestial sphere. Just understand it's not a real thing, but it's really helpful for us to understand how the night sky moves and for us to kind of position ourselves relative to the stars. So if you project it out, the celestial sphere, notice that it projects out directly from the Earth's north pole and the Earth's south pole to hit the north celestial pole up here and the south celestial pole down here. And the Earth's equator also spans out to hit the celestial equator. Okay, so all the stars, in this case it kind of looks like snowflakes, I know, they appear to reside on the celestial sphere. So notice that the north celestial pole, that is going to be pointing directly above Earth's north pole, and that is pointing towards Polaris. So notice that our Earth is spinning on this pole. Now, the celestial equator comes directly out from the Earth's equator, but our Earth's axis is tilted by 23.5 degrees. You have to imagine that this blue line of the Earth is actually tilted 23.5 degrees. That means the plane that the Earth rotates around our sun, okay, is actually tilted up relative to the celestial equator. That means the sun's path around the celestial sphere appears to be elevated above or below the celestial equator by 23.5 degrees, okay? That's exactly equal to the tilt of our axis. So the stars don't actually sit on the celestial sphere, they just appear to. The stars are actually different distances away from us. Even though they appear to be lying on the same plane, they're actually nowhere near each other. Okay, so constellations, although they look like they're patterns in the sky, really have nothing to do with each other. They're nowhere near each other typically. Okay, so if we wanted to measure angles in the sky, now you see that we look at our sky as this round sphere, okay, because we have a round Earth. So when we talk about measurements in the sky, we have to use angles. So astronomers use angles to measure the distance, apparent sizes, and distances between objects. So an angular distance is just the distance between two objects measured in degrees because we're talking about a sphere. Okay, so what does this mean? So if we looked at our horizon, okay, where the black surface here meets the sky, okay, and we went from our horizon to directly up overhead. So if you point directly up anywhere on Earth, we call that the zenith. It's 90 degrees straight up. So notice that your horizon, from horizon, let's say north, all the way to horizon south, makes a full 180 degree curve. Okay, the complete circle would be 360 around the sky, where straight up is 90 degrees. And that's what we call our zenith, straight up. So if we looked at this angular size then, we could look at the distance between two stars. Let's say the Big Dipper in the northern hemisphere, the two stars of the pot part of the Big Dipper is about 5 degrees apart. The two stars in the Southern Cross in the southern hemisphere have an angular measure of about 6 degrees. So how do we make these measurements? Well, you have a really handy measuring tool on your body. If you put your arm straight out, okay, so don't lock your elbow, put your arm straight out and hold a fist. The distance of your fist, okay, from side to thumb, measures about 10 angular degrees. So that means if you have your arm outstretched and you measure from the horizon, where the land meets the sky, all the way up to straight above, you should count about 9 fists to equal about 90 degrees. So you can use your hand as a measuring device in the sky, which actually comes in pretty handy. Because let's say you see a star and you're not quite sure how to tell your friend where to look. Well, you could say, oh, look directly south and go 30 degrees up from the horizon. And you can measure that using your hand and your outstretched arm, as long as your arm is straightened perfectly, okay? So your index finger measures about 1 degree, so you can get fine-tuned there. Your fist is about 10 degrees, and from pinky to thumb measures about 20 degrees across the sky. So I want you to measure the room where you're sitting in. So from wherever you're sitting, I want you to measure the angular distance between the floor in front of you and the ceiling. Okay, so wherever you're sitting, stretch out your arm and measure from floor to ceiling. You could actually post your answers in the discussion board this week and see what some of your other classmates got. See how similar your answers were. If you're by yourself, try measuring the floor to ceiling from where you're sitting, and then get up and either move closer or further from the wall. And what do you notice? And why do you think there's a difference? I'd like you to think about that for the rest of this week. So when we talk about angular sizes, we look at the sun and the moon in the sky, and they actually appear similar in angular size. But we know the sun is a lot bigger, okay? It's about 400 times larger than the moon in reality. But what's important is that the sun is farther away. So if you tried the example of getting closer to the wall and further of the wall, you could actually experience this difference, okay? That the closer you get is going to change the angular size that you see, and the farther you get, the angular size is going to change. So when we want to get a little bit more fine-tuned in terms of our angular sizes, we can take the degree and subdivide it into arc minutes and arc seconds. So there's 60 arc minutes per 1 degree and 60 arc seconds per 1 arc minute. How many arc seconds then are in 1 degree? Take a minute to think about that. So if we looked at the angular size of our moon, we would see that the angular size, meaning the diameter in angular measurements, if we took your hand and measured the moon in the sky, is about 31 arc minutes, okay? or that's equal to about half a degree. So check it out when you see the moon next and see what angular size you measure of the moon using your handy measuring tool of your outstretched arm in fist or fingers. So recall, whenever we talk about measurements in science, we have to think about the units. So the measurement on any physical property must be expressed both in the terms of a number and the unit. So a unit is just the well-defined value of a measurable property. So we've been talking about meters, kilometers, astronomical units, light years, and parsecs, right? Now we've added angular degrees, like degrees, arc seconds, and arc minutes. So without a unit, numbers are really meaningless. Because if I said, oh look, the moon is 5. Well, 5 what? 5 degrees? 5 arc seconds? Right? Units mean everything. So you always want to add units to your measurements. All right, well, I'll stop there and we'll continue with chapter 2 next week.